Okay, this is problem 24 from your exam 1 review, and you must know the following prerequisites. The derivative of ln of u is equal to u prime over u. This u prime is the derivative of u. Then you must also know this inverse relation. E to the power ln of u is equal to u. That actually comes from this. A to the power log of b to the base a is equal to b. So here our ln has a base of e, that's understood, right? So e to the power ln of u simply becomes u. Okay, and then the properties of logarithms, which I'm going to mention as we go along. Okay, so to do this problem, we will again use u substitution. So let u be equal to ln of x. You notice here that u is always some function, okay? This is our third problem where u is some function. The derivative of u with respect to x is, well, the derivative of x is 1, and we simply copy that u down. And so we can rewrite this as du is equal to 1 over x dx. Okay, so I'm going now to rewrite our problem in terms of u. The integral of 6 to the u. Let me rewrite this problem so that you can see this form actually, okay? So 6 to the power ln of x over x dx can be rewritten as the integral of 6 to the power ln of x times 1 over x dx. It's simply multiplication of fractions. You know that any number is understood to be over 1. So when I multiply these two, I will get this original problem. 6 to the power ln of x times 1 is 6 to the power ln of x. X times 1 is understood to be over 1 here, is equal to x. Now, we did that so that we can easily show that the problem is 6 to the u, and what is 1 over x dx? That's your du. Again, we will need to change the limits of integration. These are the limits involving x. So to change that, we will say let x be equal to 1. I am changing the lower limit here in terms of u now. So u is equal to ln of x, ln of 1. There you go. First property of logarithms, ln of 1 is equal to 0. So that 1 in the original problem becomes 0 in the changed integral. Now, when x is equal to 2, then our limit simply becomes u is ln of 2. Okay, now we're going to integrate this, but to be able to do that, we will use this fact, okay? Why? Because we only know how to integrate e to the u du. So we will integrate this by way of the integral of e to the u du. So here we go. So 6 to the u can be written as, here we go now, e to the power ln of 6 to the u. Okay, I'm just using this property here. E to the power ln of 6 to the u is 6 to the u. Now, using again another property of logarithms that says the logarithm of b to the c is equal to c times log of b, I can now rewrite this as e u ln of 6. So that power u becomes a factor, u times ln of 6. So now we can rewrite our problem as, here we go, 0 to ln of 2. 6 to the u becomes e to the power u ln of 6 du. So this is now of the form e to the u. We just have to verify what's our du here, okay? Since I'm already using u here as my variable, I'm going to use another variable. Let w be equal to u ln of 6. Now, what kind of function is this? It is a linear function because u has a power of 1. So this is actually a line. If you graph this, this will be aligned with the slope of ln of 6. And so what's our dw here? Well, that's going to be simply ln of 6. That's the derivative of w with respect to u, which we can write as let's see now. So d omega or dw is equal to ln of 6 du. Okay, so you notice here that our du does not contain ln of 6. Okay, so we will have to remove that ln of 6, and so our du now becomes dw over ln of 6. So rewriting our problem, we get e to w, and du becomes dw over ln of 6. Now we can pull out that ln of 6 because that's a constant, and so our problem becomes 1 over ln of 6 e w dw. And using our problem here, our equation here, that's e to the u plus c, then this becomes 1 over ln of 6 e to the w. Now I'm going to change my w to u so that we can use back our original limits here. So this will be written now as 1 over ln of 6 e to the u of ln of 6, evaluated from u to ln of 2. So I am sorry, but there are so many variables here, but I hope you can follow through. So what I'm going to do is copy this down here, 1 over ln of 6 times e to the power u times ln of 6, evaluated from 0 to ln of 2. You recall that e to the power ln of u is equal to u. That's from our earlier prerequisite, right? So I'm going to rewrite this as 1 over ln of 6 times e to the ln of 6 to the u. I'm using there this property of logarithms. Logarithm of b to the c is equal to c times log of b. Okay, so that is multiplied. It now becomes the power of the argument. Okay, so this thing now simply becomes 6 to the u based on this. Okay, so 1 over ln of 6 times 6 to the u, evaluated from 0 to ln of 2. And so we get 1 over ln of 6, 6 to ln of 2, minus 6 to the 0th, and we're done. We will simply rewrite that as 6 ln of 2 minus 1. Is requiring these two prerequisites. Yeah, you must know the definition of the trigonometric functions. So let me go through them quickly. Sine is opposite over hypotenuse. So if you have a right triangle here, the sine of this angle is opposite over the hypotenuse. A cosine is adjacent over the hypotenuse, and tangent is opposite over adjacent. Another prerequisite that you must know is the property of inverse trig, and I'm putting here something that our TA Cyrus put in the discussion. Secant of secant inverse x is equal to x if the absolute value of x is greater than or equal to 1. If you look at the problem here, that is obviously we will assume that that is greater than or equal to 1. Okay, so here we go. To work this problem, you must realize that whenever you have this expression arcsecant, arcsine, or arctangent, they represent an angle, right? So this expression right here is actually equal to some theta. So let's write that here. Theta is equal to arcsecant of x squared plus 9 over x. To illustrate this more clearly, if we say, what is arcsine of 1/2? Okay. Well, we know that this refers to an angle whose sine is 1/2. And that angle is pi over 6 or 5 pi over 6, because the sine of pi over 6 and the sine of 5 pi over 6 is 1/2. So, but with the definition of the arc sine, we can only use angles from negative pi over 2 to pi over 2. Okay? What I'm saying is, though this is equal to 5 pi over 6, we will normally put simply pi over 6, because pi over 6 is within the range of the arc sine function. Okay? So here we go. So, using now this property here, if I get the secant of both sides, assuming that this expression here is greater than or equal to 1, then that simply becomes secant of theta is the square root of x squared plus 9 over x. And that represents this triangle here. If this is our theta, secant is the reciprocal of cosine, and cosine is adjacent over hypotenuse. So this is going to be the hypotenuse, and this is going to be the adjacent side. So I will put that here, square root of x squared plus 9 over x. Using Pythagorean Theorem, we can find an expression for this one here. So a squared plus b squared is equal to c squared. You know that the hypotenuse is always c. This could be either a or b. Now, I normally would call this b for the base, and this is a for the altitude, okay? But they can be interchanged. So we want to solve for a. B is x, it's going to be squared, and c has to be squared as well. When we do that, the square root sign will go away, and we get simply x squared plus 9. And because x squared appears on both sides, that simply is equal to 9. And so a is equal to plus or minus 3. But because a is the side of a triangle, then we choose the positive 3. So now, look at the problem. Tangent of arc secant of the square root of x squared plus 9 over x, which we said is theta. So the problem is actually tangent of theta. And what is tangent of theta? 3 over x. Okay, so this problem requires that you are familiar with the 3 different types of integral formulas here that we wrote. We proved some of this in class, so but by this time you should know already how they appear and how they are derived. Okay, so our goal is to rewrite the original problem into something like this, one of these 3. Okay, to be able to do that, we will need the property of 0. And what is this? If I add 0 to any number a, the answer is still the same number a. Adding 0 doesn't change the value of the quantity. And then completing the square, if I have ax squared plus bx, to complete the square, when I say a square, this must be of the form either a plus or minus b squared. Okay? And so it must have a middle term. To create the middle term, what we're going to do is, to create the term here at the end, we're going to divide b by 2 and square it, okay? So that's how we will square, we will complete the square. Factoring, this would be something like this, a plus b over 2 squared. And when you expand this, that should equal to this trinomial. Okay, here we go. So, obviously, this expression here, this trinomial, is one of this. Okay, it cannot be the arctan because there's no square root. So, it could be either arc sine or arc secant, but we notice that there is no outside function here. There's no outside u. So by default, this must be an arc sine problem. So we're going to rewrite this into something like this. Here we go. Negative x squared minus 14x minus 40. Well, I noticed that if I add a 9 and subtract a 9, I'll be able to transform this into a perfect square. So if I subtract a 9 and add a 9, I'm literally adding 0. So I'm not changing the value of this original trinomial. Writing that now, I can say minus x squared minus 14x minus 49 plus 9, which I can rewrite as 9 minus x squared minus 14x minus 49. You know that this should still be equal to the original trinomial, and we can verify minus x squared minus 14x minus 49 plus 9 is minus 40. But look what I'm going to do. I'm going to rewrite this as x squared plus 14x plus 49. Again, this should equal the original trinomial. If you remove the parentheses, this will become negative and we get the original, which we can write as 9 over x plus 7 squared. Okay, now we can rewrite the problem as dx over the square root of 9 minus x plus 7 squared. So you can see that this is your a squared and your u squared is x plus 7 squared. So we can write a is 3 and u is equal to x plus 7. So the problem now becomes arc sine u over a, so x plus 7 over 3 plus c. Your answer. This is problem 38 of exam 1 review, and if you notice, the function is a product of two functions. One is a linear function, 8 minus 8 theta is linear, and the second function is the hyperbolic tangent. So this is a derivative that will require the use of product rule. The product rule says if we want to get the derivative of f times g, which are two differentiable functions in terms of x, then we can go f prime times g plus g prime times f. It doesn't really matter which order you go because addition is commutative. Okay, so we get the derivative of the first function times the second plus the derivative of the second times the first. Also, we need to use the derivative of hyperbolic tangent u, and it's given as u prime over 1 minus u squared. I am allowing you to use this formula in the exam because we just took hyperbolic functions as one section and we didn't have all the time to prove all of these beautiful results. Okay, so you can use the formula sheet for hyperbolic functions, except the integral part, which we will discuss in chapter 8. Okay, for the time being you can use all of those. Here we go. So y prime is equal to the derivative of 8 is 0, the derivative of negative 8 theta is negative 8 times hyperbolic tangent of theta plus, we now copy the linear function 8 minus 8 theta, and the derivative of hyperbolic tangent theta is equal to the derivative of theta, which is 1 over 1 minus theta squared. So all we will do is simplify this, and that's it. Okay, so negative 8 times hyperbolic tangent of theta plus, we can write this as a single fraction, 8 minus 8 theta over 1 minus theta squared, and then we can do some simplification here, algebra. Okay, here we go. Negative 8 hyperbolic tan of theta, we can factor out the 8 in the numerator and we get 1 minus theta. The denominator is a difference of two squares, which is factorable into 1 minus theta times 1 plus theta, and so your final answer is negative 8 hyperbolic tan of theta plus 8 over 1 plus theta. You can write that in another form by factoring out the 8 and say 1 over 1 plus theta minus hyperbolic tan of theta. Answer. I apologize, I just realized that I forgot writing the h. So it should be 8 times 1 over 1 plus theta minus hyperbolic tan. Inverse hyperbolic tan, okay? Theta. So I forgot the h there. So we are asked to find the limit of arc cosine x as x approaches 1 from the left. To be able to find the limit, we will review the graph of arc cosine x. Okay? So we recall that the function cosine is not 1-to-1. If you recall, the graph of cosine is something that looks like this. That's one complete period from 0 to 2 pi. So you know that the cosine keeps on going in both directions. And so if we do the horizontal line test, that will fail the horizontal line test, and so it's not 1-to-1. And so what did we do? We restricted the domain from 0 to pi so that the graph becomes 1-to-1. So this is now the 1-to-1 cosine with the restriction of 0 to pi. There you go. Now, because it's 1-to-1, we can graph the inverse. To find the inverse, we simply interchange the x and the y. So instead of writing y equals cosine x, we will write this as x is equal to cosine y. And to get y by itself, we will say arc cosine of x. So this is from trigonometry, okay? Now, to graph the inverse, you recall that when two functions are inverses of each other, okay, their composition is equal to x, right? This implies that f and g are inverses of each other. This is from algebra, okay? And it goes both ways, g of f, and these are equal to x, okay? Graphically, two functions are inverses if they reflect each other over the line y equals x. So this is y equals x. And if your f function looks like this, okay, then your g function should look like this. Okay? They mirror each other with respect to the line y equals x. I'm sorry, my graph is not really accurate. I should have graphed the other one much slimmer this way. Okay? So, using now our graph for cosines, 1-to-1 cosine, the graph will become, so this is now the graph of arc cosine x. So you recall that this is our x and this is our y. This is from -1 to 1, and the x values are from 0 to pi. Well, when we do the inverse, we will also switch the x and the y. This now will become 0 to pi. Okay, here we go. This is pi over 2. And 1 to -1 will be here. So this will now be your -1. And this will be your 1. So graphing this onto this, remembering the fact that they reflect each other over the line y equals x, then my graph should look like this. There you go. That will be the graph of the arc cosine of x. Now we're approaching 1 from the left. This is 1. We're approaching from the left from this direction. So the value of y is 0, and so we say the limit is 0. Supposing now that the problem says find the limit of arc cosine x as x approaches -1 from the right. Our original problem was as x approaches 1 from the left. Well, in this case, -1 is here coming from the right. then the limit will be equal to pi. Because as I approach negative 1 from the right, the value of y goes to pi. Another one. Supposing that the question is the limit as we approach negative 1 from the left. Where is negative 1? This is negative 1 from the left. Well, unfortunately, we cannot approach negative 1 from the left. So the limit here does not exist. There's no way I can approach negative 1 from the left because the graph stops right there. Another one. What is the limit of the same problem as we approach 1 from the right? Our original problem is as we approach 1 from the left. Well, as we approach 1 from the right, there's no way I can do that. The function is not defined beyond 1, so this one does not exist. Let's find the limit as we approach 0. Now you notice that I did not qualify whether I approach 0 from the right or from the left. It turns out that 0 is defined from on both sides. I mean, I can approach 0 coming from the right, I can approach 0 coming from the left. So in Cal 1, we call this the limit exists because the limit from the right is equal to the limit from the left, right? But in this particular case, the limit is pi over 2. As I approach 0 from the right, the value of y goes to pi over 2. As I approach 0 from the left, the value of y approaches pi over 2. So the limit as x approaches 0 is pi over 2.